Hello, everybody. Here I am glad to introduce Professor Bart Kosko. He's a professor of electrical and computer engineering and law at University of Southern California. He holds degrees in philosophy, economics, applied mathematics, electrical engineering, and law. Dr. Kosko has published the textbooks Neural Networks and Fuzzy Systems and Fuzzy Engineering, the trade books Fuzzy Thinking, Heaven in a Chip and Noise, the edited volume Neural Networks for Signal Processing, and the co-edited volume Intelligent Signal Processing. And also the novels Nanotime and Cool Earth. We are very familiar with his great work, and we are wholeheartedly welcoming him to give his presentation entitled Rule Mixtures and Fuzzy Cognitive Maps, Advances in Feed-Forward and Feedback Fuzzy Systems. Thank you.
Thank you, Barnabas. The talk is on rule mixtures and fuzzy cognitive maps, and I'm aiming this talk in particular at the younger fuzzy researchers. I want to help make that case that the fuzzy research field is alive and well. It's not in jeopardy, and it's certainly not moribund. Here's an overview of the talk: feed-forward and feedback systems. What do we mean by that? In the simplest sense, in a feed-forward system, if you put in an input X, it flows right out like water out of a pipe, comes out Y. Whereas if I put in X in a feedback system, the output feeds back in as input. Now, my claim is that we can represent ordinary fuzzy systems, they turn out to be additive, as generalized probability mixtures, which I'll explain. Fuzzy cognitive maps are more complicated structures because of the feedback that the causal arrows produce. So for example, this is a cognitive map from a paper on my website at USC, and all this material is on my website at USC, dealing with pods or herds of dolphins. And if a shark appears when the dolphins are resting, a survival threat, then that will decrease the amount of rest, it will increase their running away, and so forth. Even a simple five-node cognitive map has very complicated dynamics, and you have to analyze them and use them in a different way. More broadly, I want to point out that one of the main criticisms of fuzzy systems from at least AI researchers is that fuzzy systems are not in the language of probability, that probability is enough. That argument collapses at the outset when we can completely describe, as we now can, additive fuzzy systems, which are the overwhelming majority of fuzzy systems that have ever been applied in control and elsewhere, describe them completely and extend them in the language of probability theory. I want to start with a little background because I want to focus on additivity and at the same time remember what the whole research program is about, and that's the concept of a fuzzy set of shades of gray of matters of degree. And here is where I first really started thinking about that. I was graduating with a degree in philosophy and also in mathematics and economics, philosophy and logic. And I had a student subscription to the Journal of Philosophy. I got that February 1981 issue, and there was an article by philosophy grandmaster from Harvard University, Quine, Willard Van Orman Quine, or Van as he liked to be called. And he had an article with this interesting title, What Price Bivalence? What's the cost of using black and white? I must admit, like most people, I really hadn't thought about that, although I was training extensively in black and white logic. And here are the two sentences that really changed my life, where Quine went back and looked at that table that his predecessor, Bertrand Russell, had looked at in his book, The Problems of Philosophy, the to be or not to be question when something is or is not a table. If the term table is to be reconciled, he said, with bivalence, we must posit, we must assume an exact demarcation, exact to the last molecule, even though we cannot specify it. Just think about that for a minute. We have to assume everything is black or white, and we can't actually draw that line. We must hold, he said, that there are physical objects coincident except for one molecule such that one is atypical and the other is not. Now, Quine believed that that cost, which he admits is high, was worth it. His example was his definition of a mountain. I'm not going to read it to you, but there's a lot of very arbitrary and precise terms, like 1,000 feet. And so if we're epsilon a little bit less than 1,000 feet, are we suddenly not a mountain? It's a very high cost. Who draws these lines? What happens when we have perturbations about the borders and so forth? That's at the very heart of fuzzy logic and fuzzy theory, no matter how we formulate our systems. And I'll show you next an example that I've spent a lot of time thinking about, and I discussed in my earlier book, Fuzzy Thinking. And it goes to the heart of an ongoing controversy, at least in the United States, and that is the notion of abortion. When does life begin? When do we go from not life or death to life? Now, the United States Supreme Court, in what was arguably the most controversial decision of the 20th century, said, in effect, it begins at the first trimester, at 3 months. They drew a line, or at least suggested you could draw lines on a trimester basis. It's kind of interesting, it all works out easily divisible by 3. The other argument, the other side of this, the more extreme view of pro-life or pro-choice, would draw the lifeline exactly at conception. That has advantages and a lot of costs. And the other extreme, the extreme pro-choice, say, nope, exactly at birth, 9 or so months. Also, benefits and costs. It's not my point to argue for those benefits or costs, but simply to draw your attention to the logic of it, to the binary logic and the controversy this has caused. Nobody's happy with how someone else draws those lines. By the way, the decision was modified in 1992 in the Casey case to something called viability, and we don't know where that is. Now, the obvious fuzzy alternative to this is to draw a curve instead, something that's monotone increasing with gestation. And you can estimate that curve. It still surprises me to this day, we don't seem to have done that in this country, through simple polling techniques, through an additive technique. So for example, you call people up at random, a sufficiently representative sample, and you say, what month do you think life starts? If you say it starts at month 5, we would put a 1 in that slot in the vector, and also for at 5, 6, 7, 8, 9, and zeros before. Add up all the vectors of all the people you polled, divide by the number you added, and you'd get this stepwise approximation to the US life curve. I'm not saying this solves the issue, something as contentious as to be or not to be when life begins, but it is an advance of sorts, and it has nothing on its face to do with probability. We can certainly put probability on top of this. We can talk about the probability that the knee in the curve occurs at 5 months and so forth, but that's a separate type of uncertainty. All right, let's get back to mixtures here. I'm keeping that fuzzy structure, that essentially new thing that comes with fuzzy theory, a fuzzy set, and reasoning with it, and focusing now on the logical consequences of additively combining rules. And my claim is that gives you these probability type surfaces you're looking at in these carpets down below. Now in this case, I have 2 separate fuzzy systems, each with 10 rules, and their goal is to approximate sine of x, here just from 0 to 2 pi, but in general over the whole range of the real line. So in modern AI terms, this would be a regressor rather than a classifier. I'll get to the classifier in due course. Now, each of these systems fully approximates, very quickly approximates sine of x. Each uses 10 rules. The sync system uses rules of the form sine x over x, which we have found for at least a quarter century is often the best way to proceed from a purely function approximation point of view. It's still unclear why that's the case, but in the question, what's the best shape of the if part fuzzy sets, I would always, as a knowledge engineer, keep that in my toolkit. Gaussians often work well too. I get somewhat different surfaces. Each has 10 rules, and that will correspond to mixing or weighting or combining 10 probability curves that will give back sine of x. The more general theorem is illustrated here, and it has extensions. And that theorem is this: I can do more than just approximate sine of x with one of these mixture waveforms. I can exactly represent it, hit it 100% on the head, on average, by mixing just two bell curves, normal bell curves. And I'll show you how that's done. This also, by the way, I think makes an excellent teaching tool and examination tool, but we'll get to that. Sine of x is bounded between 1 and -1. And if you'll note, I have two bell curves, one in red and one in blue. The first one in red centered at -1, centered at the infimum of sine of x, and the second one centered at +1 at the supremum. I've picked an arbitrary value, x0. It fires, and technically it fires, not in some vague way, but by convolving with a delta pulse. But I'll leave that to the mathematical details. You can look at in the papers. I pluck off the value at 3.1 something, if you see that in light green, and I end up with a mixture by carefully picking, and I'll show you how to do that, the mixing weights, the convex combination weights that are non-negative and that add up to 1. For these two bell curves, I get this green bell curve. And if I take the average of that, that gives me back sine of x at that point, not approximately, but exactly. This is very much like quantum mechanics. I'm not saying it is quantum mechanics, but it's like it. Quantum mechanics is a very linear theory. What we observe are the eigenvalues of Hermitian operators, and those turn out to be averages, the averages of those values. And that's what we're observing here. The entire structure of the function representation is captured in this probability carpet, and it gets realized like a wave function collapsing upon measurement into a particular value. What's the point? The point is the output of the fuzzy system is the average, the conditional expectation at a particular value x. The only condition on this theorem is that the function you're estimating be bounded and not constant. If it is constant, like f of x equals 3, this is all trivial. You can do it with one rule. What about if the function is multivariate? No problem. This applies component-wise in the vector. Now, if I go back to the traditional view of fuzzy systems, the way we often interface with users, then I get something like this. Sets are defined by words. Words and sets go hand in hand. Collections of sentences define systems. This is from the fuzzy air conditioner that I discussed in my 1993 Scientific American article on fuzzy logic. It's a very intuitive fuzzy air conditioner. If the air is cold, set the motor speed to stop. If the air is cool, set the motor speed to slow, and so forth. So this is a classic example of what Lotfi called computing with words, of programming a system in natural language. It's not the only way to go. The new advance here is to see that there was a probability mixture description all along. We simply missed it. We'll get to this. The first step up, though, is to realize those rules. If the air is cool, let the red set be cool air. Then at the motor speed is slow, let the motor speed and RPM be the dark blue triangle over here. Those form in the input-output product space, here the plane, this purple rule, blue and red combining to form a rule or a rule patch. I get function approximation by covering the graph of the function. But what is learning in these cases? It's anything that moves the patch. It's the movement of the patch. And I can do that in particular with parametrized fuzzy sets by changing, for example, their mean or median and their dispersion. So here I have a very potent fuzzy if-part set, not often used in applications. And that is the double exponential or the Laplacian. You might also see that in statistical regression in what's called lasso, for example, and many, many other cases. But look how complicated it is. The new location parameter, the mean, if you like, of the Laplacian, is the old one plus all this other stuff. And the dispersion is, the new one is the old one plus all this other stuff. We get a kind of, not rule explosion, but a computational burden that's very, very high to tune a traditional fuzzy system. And there's a bigger problem. the very nature of these rules is that they are graph covers. That gives us relatively easily theorems about uniform function approximation. The earliest one I published in my 1991 textbook, Neural Networks and Fuzzy Systems, and many versions thereafter. But the intuition's clear. If I want to approximate a function, I can cover the curve with rule patches. And in the first case, I have just one input variable of temperature. If I want a better approximation, I add more rule patches. What happens though when I try to make the model more realistic and add another variable like humidity? That would be the y variable. Well, the number of rules I need starts going up, and I get this exponential rule explosion. You really can't have it both ways. You can't have the function approximation power that is inherent in the patch cover and the concomitant cursive dimensionality, the exponential rule explosion that is also hiding there. I'm going to return to how we can mitigate that with the mixture approach. Now, optimally, you can show, if I had a lone rule, the best place to put it is at a turning point of the function. That's sometimes phrased as patch the bumps. This is an inherent problem, the system. We often formulate, and at least in a diagram, and this is more of a 1990s way of thinking about fuzzy systems, as a fuzzy associative memory, in the sense I have an input X, it applies and activates M many rules by firing partially the if part sets. Again, technically that is a convolution with the delta pulse. And the fired then part sets, B1 prime through Bm prime, add. They don't take the maximum, they add together. And then this awkward term, I quote, defuzzify the output set B, and I get the system output f of x. And sometimes we use the word to fuzzify on the front, on the back. That's a very ad hoc approach. It does summarize the systems out there. There's a more general way to do it, as we'll see in just a moment. And that is precisely where mixtures come in. But it's quite powerful, at least if you have only a few dimensions. Here I have a target function, the upper left panel, with 12 bumps, and I start off tabula rasa, a blank slate fuzzy system, and very quickly it approximates by patching the bumps, basically, quickly approximates here, I think it's fewer than 100 rules, the test function. And then if I'm willing to pay ever higher cost of more and more tuning, I get a finer and finer approximation. There's something else though going on. I want to be able to go from the rules here on the left. I've got 16 of these patches. I'm using M for M many rules, M equals 16, to what I now have on the right, which is a weighted sum of M many likelihood probabilities. I'm going to go into more detail in just a moment on that. But this is the big picture structure, the advance here, going from what's on the left. First, we have linguistic rules, and we started thinking about them algebraically and geometrically as patches. And now, increasingly, I think we'll see the mixture approach. At least that's my claim. And we'll get back the old systems as conditional expectations that are realized. In other words, even it was clear for at least 3 decades or more now that a fuzzy system output f of x simply gives you a convex combination of the centroids of the then part sets, the BJs in this case. So the mixture looks like this. I am mixing those same PJ weights that we've been using for quite some time, but I also now have on the right these likelihoods, and these turn out to be familiar terms in probability. On the left, I have prior probabilities. On the right, I have likelihoods. Now, normally, when you're mixing probability curves, for example, in a machine learning course, you use mixing weights that are constant. Here, these are generalized because the mixing weights depend on x. In other words, for each input x, I have a different set of m many priors, and they add up to 1. And likewise, the likelihoods, the outputs given x, probably b sub j indexed here by the then parts of the rules. And this is what the weights actually look like. I want to stress here a clear break, though, with the past and the older fuzzy formulations. And that is, this does not hold for min-max or max-min systems. It does not hold. You don't get this additive structure. And incidentally, even though some of the older papers in the 80s might talk about a min-max structure for fuzzy systems. I'm talking systems now. Now, you'll see in the actual applications, they were additive in combining them. The big picture here is that what I'm really looking at, what the fuzzy system's really giving me, is the fundamental theorem on total probability. But why do we get the mixture at all? If I take rule firings in general, as long as they're non-negative and integrable, and divide by their integral, so I'm dividing by an integral, integrating out y, the output variable, I always get a PDF that is non-negative. If I take the integral of the left side and the right side, that integral equals 1. That's not in dispute. But now if I go further and make the assumption that what I'm doing is adding fired then part sets, and that's what bj of y given x does, I can invoke this sum. The sum commutes easily and non-problematically with the integral. I invoke the volumes, which are just integrating over the regions of the then part sets. And a little bit of algebra and rearrangement, I end up with these weights, these convex combinations of these likelihood functions. So the structure of the rules, the then parts captured in part in the likelihood, but also it's bound up in, because of this weighting function, in the priors. And that's the result. Again, this is new in Revelation. We're seeing it now. It's always been there. We simply missed it. And what are we looking at? We're looking at a probability, let x be fixed. We can always take an unconditional probability and expand it to the theorem on total probability. And we can index that by the input x here. We're looking at a sum of priors and likelihoods. And that theorem gives rise to a corollary with that odd name, Bayes' theorem. And this is important. So Bayes' theorem will always have the form of A over A plus B, which is in this ratio. And that's exactly what I have. I suddenly get a blow-by-blow, input-by-input description of how much each rule indexed by j fired. So P of j is the probability that the jth rule fired, the degree to which the jth rule fire, given any input x. And by the way, there's no condition on what x is here, any kind of input space, vector or otherwise. And it emits an output that's observed y. So I fire the system, I have an output y, and I say, okay, which rules contributed what? The answer is on the right. That is a complete posterior probability distribution of the inner workings of the fuzzy system. It opens many doors, including a way of doing explainable AI, because we at once get to interpret the rule base. And it goes much further than this, as I'll show you. We can combine multiple systems and still get posteriors over the systems and over their subsystems. Now here's an example applied to classification. I have another paper here at the NAFIPS conference on, we call random foams I'll come to, but here's a case where I've got 1,000 fuzzy rules, if parts are Gaussian, so foam systems I'll discuss. And I'm training on the 10 SciFar images in the standard test case. And when I take an image of a deer, it fires, in theory, all 1,000 rules to some degree, but really only 5 of them to non-zero degree. And rule 616 fires the most. And if you kind of peer into it, you get some further interpretation. You can see the if parts of that rule look a lot like a deer. It opens up a lot of opportunities at once for pruning strategies, for adaptation strategies, and just the straight up ability to analyze the inner workings of a black box, especially when, as you'll see, and as we do, when we train on a black box neural network to begin with. Well, what about that old action we did of fuzzification and all that business, that 90s talk? Let's start now with the firings. And in this formulation, I'm not even using here the additive structure. Again, a non-negative B that's integrable. That instantly defines a conditional probability. And so when I integrate that out against y, I get a conditional probability. and I back up through that, and out comes my f of x. I don't need this ad hoc defuzzification or fuzzification. The rules give me at once the mixture, and the mixture's got a lot more information in it. And I can go the other direction. I can start with a mixture and get a system out of that. When I have a mixture, I get more than the first moment, the expected value. I get, in theory, infinitely many higher order moments and infinitely many fractional lower order moments. But the one I care most about here is the conditional variance or covariance in the vector case. It gives me a natural description, again, blow by blow, of the uncertainty in the rule-based system. I don't need to add other things. I don't need a type 2 or any other type system here. This information is available, and it's the same information that I need in order to compute f of x. We've simply been ignoring that, and we've been using these for some time. If I want more higher order moments, I can get them. These are integer moments. What happens with an additive system in terms of the output? When, in terms of the uncertainty, if I ask it a question x, I get an output, and it breaks into two pieces in terms of its uncertainty, the ball of uncertainty, an inherent uncertainty tied to the then part sets. The older fuzzy applications, especially in the commercial products out of Japan, simply ignored then part sets and often replaced them with a spike. That would represent total certainty. These variances here would be essentially zero. But that matters. Different shapes of then part sets should affect it. On the right side, I get the interpolation penalty. So the fuzzy system tells me, blow by blow, when I ask it a question, not just what its answer is, but how confident it is of its own answer, given what it has learned, given the M rules in it. You can use that for a lot of purposes. Here's a simple example where we trained on two pattern classes, red and blue. And we notice that where a misclassification tends to occur is precisely where the conditional variance is highest. And again, you can use that for a variety of purposes, pruning and otherwise. Let's get back to this example. 10 rules, if the if part sets are Gaussian, I end up, after a little bit of training, with this system below this curve. And its average gives me back this mixture, mixing 10 likelihoods. It gives me back sine of x, at least to a high degree of approximation. Now, it also has, again, a Bayesian posterior over the rule firings. So I can see in the middle panel the 10 rules in terms of the centroids and then part sets, kind of laying out very neatly the sine of x. And if I take this panel where I've taken an input of pi halves, I know the output is going to be 1, and I see that only 4 rules are fired, and so on. So I get a blow by blow. So if you're going to use a fuzzy system, if you're going to, in a legal sense, turn it loose on society, to put it into the stream of commerce, for goodness sakes, check its conditional variance and study its rule-based structure. And I think you'll also find it'll stimulate your own creativity of many, many algorithms you can come up with using this information. The general theorem here, again, it's in the papers, my webpage, and elsewhere, is a kind of mixture extension of the Watkins representation theorem. The result is I can always represent exactly any function it's bounded, as long as it's not a constant, by centering probability distributions, in particular standard normal or ordinary bell curves with arbitrary variances, centering them at their infimum and supremum, as long as I carefully pick the weights. And I call these Watkins coefficients in honor of one of the great theorems of the fuzzy field that's been wholly ignored, so far as I can tell. Dr. Fred Watkins is a mathematician and an expert in C-star algebra, among other things, and he came upon this many, many years ago, decades ago, when he was analyzing just what sorts of functions can be represented at all with an additive system. A lot can't, and he came up with a necessary and sufficient condition in terms of a partial differential equation. But one consequence was this uniform distribution looking term for the Watkins coefficient, that I take the supremum, which in the case of sine is 1, and subtract off sine and divide by sup minus inf. And that gives me the weights. In particular, it looks like this, the Watkins coefficients. So they're convex coefficients. And when we first saw it, when this first came out in the early 90s, I discussed it in my textbook, Fuzzy Engineering, came out in 96 and elsewhere. it looked like a circular way to do function approximation. After all, if we're trying to approximate the function on the left, we don't need to do it if we know what it is. But we overlooked a lot of applications. For one thing, even in the Watkins theorem case, we were able to represent any bounded function like sine of x, but almost any probability distribution you'll ever look at with just an additive system with just two rules. This mixture result collapses back to the Watkins result in the deterministic case when the variances of the bell curve go to 0, because then, as you know, the normal bell curve tends towards a Dirac delta pulse. And that's the classic Watkins representation theorem. So it turns out you could represent a lot of things, for example, the kinds of posteriors and priors and likelihoods used in Bayesian analysis, and a lot more. So now I can show you again where we began. Here's my case of sine of x, now represented in accord with that theorem by centering two bell curves. I picked them to have unit variance just for ease of observation. They don't have to. And by mixing them with the Watkins coefficients, I get this green line, which is a particular curve, mixed curve, for a particular input x. And again, the output is precisely sine of x when averaged. This is what it looks like when you go through the exercise. An excellent exercise, I might point out, for examination purposes. Indeed, I've used this problem as a midterm exam question in various courses in probability and statistics. And I have to say, my finding with students is they're quite interested, provided you present the fuzzy results in the language of probability. It is simply the case again that not just in machine learning, but AI and much more broadly, the language of these sciences is probability. So consider the popular exponential distribution. Here, the unit exponential, for example, using waiting times, service times in a queuing theory model. You'll recall that this has that wonderful property that its kth positive integer moment is precisely k factorial. So the question is, if I give you this bounded function, it's bounded between 0 and 1, it's clearly non-constant, can you find the generalized mixture that represents it? Yeah, quite easily, and you're looking at it, and its conditional expectation gives that back. My question to you, the audience, how would you find the generalized mixture, and really the two rules corresponding to this, for a standard normal PDF? You should be able to do that. There's more. Let's suppose I have a fuzzy system, capital F sub n, that's converging as it learns to some target function f. It could be, in the case of a classifier, a very simple function, literally what's called in real analysis a simple function. So that such that its set theoretic inverse is precisely the pattern classes. But in general, it can be any function. The function capital F of n doesn't have to be a fuzzy system. It can be a neural network, a learning automaton, anything. And let's suppose, to make it really interesting, and the n is a subscript on the learning iterations, that the convergence is uniform. Uniform convergence means I can pick the error tolerance in advance, and it's true for all inputs. As long as I form what I call absorbing Watkins coefficients, I can swallow up this function as it's converging in the same way, and then, assuming I know the upper and lower bounds of the function, or I estimate them, and then plug that into the two normal curves, so different weights, and I come up with a simple Gaussian mixture for this. So again, normally when you will see in the literature, especially in machine learning, the word mixture, it's usually a Gaussian mixture. It's the standard way of modeling in high dimensions a surface with 10 clusters or 100 clusters. You would mix together 10 or 100 vector normal and use the EM algorithm, the expected maximization algorithm, to tune it. Here again, it's a generalized mixture. And the question is, when I've combined, I've swallowed up my converging system, and then I mix the two PDFs, will this mixture converge to the probability mixture P that encodes F? And if it does, we'll do it uniformly. Answer yes, details in the paper, but you can see it geometrically. After a few bouts of learning, I quickly got approximations of my sync system on the left and my Gaussian system on the right. Again, 10 rules each. But as they're learning, they're defining their own Gaussian mixtures, mixing two bell curves. And after a little bit of learning for the sync system, I get the carpet on top and the Gaussian on bottom, and very quickly they converge as predicted to the mixture that mixes two normal bell curves and they're indistinguishable to the eye to each other and to the normal curve. The earlier mixture here, illustrating the theorem. There's so much more to be said. There's not time here. You might take a look again at my webpage. There's a complete mathematical treatment of this from 2018. What if I have not one function like sine, but a whole bunch of them, or many of them, little f1 through fr? And what if I have q many experts? This is the old question of fusion or combination, of combining hard knowledge in equations, closed math models, with soft knowledge, like asking experts questions. Because of the function approximation power of rule-based systems, of mixture systems, I can always get a pretty good approximation of that system if I have enough data or something to help me generate or expert input the mixtures. Then it turns out I can combine all of this, the soft and the hard. If you think of, like, for example, the human models of humans, experts versus closed math form models, into one common rule base, and more generally into one common mixture with a master mixture, and you're looking at it down below. On the one side, I am mixing a mixture, the piece of rep, which is the generalized mixture that represents all the closed form math model functions, and over here, I have the rule-based approximation for the capital Q many capital F systems. And they have a mixture S put on top of them. In general, mixtures are closed. It's a wonderful property of mixtures. If I mix mixtures, I get back a new mixture. There is no end to it. Here's something else. Again, time doesn't permit me to go into great detail. And it sounds, frankly, crazy on its face. If I'm worried about rule explosion, how about completely exploding it and having infinitely many rules? And not just infinitely many rules, but continually infinitely many rules as there are real numbers. Call them rule continuum. Now, an analogy in chemistry with a mixture and compound, we replace the sum in probability for a mixture and call that a compound. We're compounding PDFs. We often discuss in a course in statistics and the like. It's a very easy maneuver mathematically, as long as things are integrable, and that will be the case as long as either one of the mixtures, either one of the probability curves is bounded. But to what end, you say? Why in the world? We're so worried about rule explosion. Why would you want to have infinitely many rules? What can you do with them? Answer, Monte Carlo. I have really a virtual rule continuum. And if I have a mixture, and we know, I showed you how to construct the mixture to encode sine of x. You see it at the bottom here. Monte Carlo, that great technique from 1947 of von Neumann and Stanislav Ulam. Monte Carlo uses the law of large numbers to allow me to estimate integrals. What's an example of an integral? An expectation. And that's precisely what a fuzzy system is, what a quantum system is. That's indeed where they came up with it, in that case in high energy physics. So what you see is sine of x in red here. And I've reached into the virtual rule continuum and I've sampled independently. So this is not a Markov chain Monte Carlo approach, although that works too. That's a whole nother lecture. I've reached into the rule box, virtual rule box, and pulled out at random 100 rules in the first case. And I get something in blue that looks like sine of x. How did I pick them? The crucial idea is I sampled according to this mixture. It's a form of weighted Monte Carlo. As you know, with ordinary Monte Carlo, it's got a big advantage and a big disadvantage. The great advantage of Monte Carlo is that it does not depend upon the input dimension. That's why it's so popular, for example, in modern mathematical finance. Because there we have very complicated portfolios, they're high dimensional, and really the only way we can get an answer is through Monte Carlo. And the idea of a price in modern finance theory is simply a conditional expectation realized. The downside to Monte Carlo is a slow convergence because of the central limit theorem ultimately, 1 over n squared, and you see that fall off. So if I increase from 100 to 1,000 samples, I get a better approximation up to 10,000, and I get a much better, and you see the slow fall off as predicted. But it's a whole different talk. The difference now is the complication is in computing a particular output. So I have to use an averaging process. But I can also now mitigate rule explosion in a whole different way by focusing on, in effect, the bigger bumps in the mixture. Different talk. Now, from an example, the classifiers, what we call a random foam. And my PhD student, Akash Panda, we have a paper on that here at NAFIPS. You can also find it on my webpage. And this is something analogous to a statistical random forest, but different. What do I mean by foam? It's a way of referring to the if part sets, especially in a neural classifier. The trouble with classifiers, when you're modeling image classifiers anyway, this way in fuzzy systems, the input dimension, number of pixels, for example, is very high, or however you try to approximate it. So if you think about the if part sets here, they're little ovals corresponding to Gaussian if parts in terms of the vector Gaussian. A natural thing to do is in a given pattern class is spend most of my rule budget on the boundaries and not so much worry about what's inside, so it looks like a foam. I've dropped from 435 to 202 rules. The idea, though, here is to take a neural classifier as deep as you like, train on data, classification data. Remember, an ideal classifier is a simple function. It's giving you such that its inverse image gives you back the k-many classes that you're sampling from. And I can form very quickly a mixture structure, a rule-based structure, we're calling this a foam because of the structure of the if-part sets, that approximates that. It forms a proxy system. If I combine these now, and I get a kind of foam forest, if I randomly form these as I sample from the classifier, in particular bootstrap sampling with replacement here, then it is very much like a random forest, which is based on trees, but we're not talking about that. And I can get some insight here. Here's the top case of the 10 CIFAR data, bottom some images from the top is MNIST data, the bottom is CIFAR. When I correctly classify the nearest if part bubble, here it looks like that car, here it looks like that horse. When I misclassify the deer I have in the image, when I get down, the frog does not look like the deer that I misclassified. So I get some visual insight, for example, into the performance of the system as I'm truly doing explainable AI. And again, I have those Bayesian posteriors that I can also use. Likewise, the variances. My last point about these foams is how you combine them. A natural thing to do, and I don't think it's the correct thing, is simply to combine outputs. That's what's done in a random forest, for example. You construct trees, and then you combine the outputs of the trees. So you ask a bunch of experts what they think, X, and they give you each an answer, F sub K of X, and you combine what they say. The additive structure allows something more powerful that allows you, in effect, to combine what they think, their brains, or the rules that we use to model them. And that corresponds to a double mixture, where the outer sum now is over the Q many experts that I'm combining, the inner sum is as before. So I'm able to get back a telescoped blow-by-blow analysis of the system. I've got here 10 systems. This is for the MNIST system. I don't have to limit it to 10, Q equals 10. I've got the different foams. I'm trying to map 3 in a classifier way, maybe with my underlying neural network or not. Here, a neural network, by the way, is not the end of the story. It's literally the beginning. It's just a means to the end of a more informed, explainable AI structure, like a random foam. And I try to map to this unit bit vector where 1 is in the appropriate 3 slot. I have 10 foams. That particular image of 3 fires all 10 of the systems, and I can see quite clearly that the third subsystem fires the most, second most, and so forth. And then I can open up, because of the Bayesian posterior structure, I can open up the system and see which of the third system's rules fire the most. See how that works? So here is the Bayesian posterior over the rules in the third system if I average out the others, I get back a master system. Modern AI seems to have moved away from expert systems, which correspond pretty closely to fuzzy rule-based systems. And more popular now is the Bayesian DAG, or belief propagation and belief trees, in particular in a causal instance. And I would refer you here to the book by Russell and Norvig, Artificial Intelligence, just out now in its 4th edition. X causes Y. Now, the first thing to note is that I have a directed graph, the arrow, and it is acyclic. There's no feedback. The second thing is that I've put a probability structure on top of this. The hard part of causality is really taking place, I think, with the arrows. The probability on top gives you a way to derive an output, a nice, precise numerical probability, if everything works. The trick is to have, for n nodes, an n-dimensional joint probability. And I can always factor that into a product of conditional probabilities with the multiplication theorem. Here, somewhat simplified because of the purported Markov effect. But I have to marginalize out a bunch of nodes in order to get the probability of a given node. And it's a long-standing result that that's a very hard thing to do computationally. It's NP hard. In general, there's no feedback here. There have been some extensions of so-called loopy algorithms, ad hoc and still small scale. You rarely will see one of these belief trees with a lot of nodes. And yet it's put forth as a model of causality, especially when we're dealing with, say, social or medical or other phenomena. But no feedback. That makes it very hard to combine. We'd like to have 10 or 1,000 or 1,000,000 experts all combine their expertise. But in general, a directed acyclic graph, when combined with another, won't give you back an acyclic graph. And finally, even if you can overcome all those problems, and sometimes you can, that's great. But in general, you can't. But if you could, we still have the question, well, where do you get this big joint PDF in the first place? I think this is partly why we see this applied at the smaller dimensional level. There is another problem I want to call to your attention. When you put a probability theory on top of this, it raises questions about the limits of probability itself. We know that causality is transitive. Logic is transitive. For example, if A then B and B then C, then if A then C. Set theory inclusion is transitive. The great example of causal transitivity is the old adage, for want of a nail, the horseshoe was lost. For want of the horseshoe, the horse was lost. For want of the horse, the rider was lost. For want of the rider, the message was lost. The battle was lost. The war was lost. I give you as an alternative in just a second, something that is transitive. But let's ask, is probability transitive? You should convince yourself that it is not in general. So let's suppose I have a set C, an event, and it contains complete subsets A and B. Then the probability of C given A is going to be 1, and the probability of C given B is going to be 1. But if A and B are disjoint, the probability of B given A is 0, and 0 does not equal 1. There's no way that's transitive. And that's still true in general when A and B are not disjoint. A very special case where you get transitivity is the trivial case where A is a subset of B, subset of C. Well, here's something that is transitive, a fuzzy cognitive map. Something I developed so long ago in the early 80s to model complex causal situations, and did so with my training really in philosophy. And back when I was working on my PhD, one of my advisors I was lucky enough to have was Lotfi Zadeh, and I would commute to UC Berkeley, if you just indulge me for a moment, and to give talks to Lotfi's group there and to meet with Lotfi, of course. And he wanted to talk on cognitive maps. He was quite intrigued by fuzzy causality. And I laid out my 50 or 60 or 70 view graphs, and he walked before the talk and looked at them. And he came up to the 15th view graph, which was this one. And he said, start with this, lose the others. And he was exactly right. So in honor of Lotfi, I thought I would start with that. This is a cognitive map that's a crude explanation of how fast you drive on a freeway, at least a California freeway. Some things affect it, like if there's a highway patrol, it'll always make you more risk averse. And a plus indicates causal increase. If you have a highway patrol, it tends to decrease, minus sign, auto accidents, and so forth. Even here, we get little causal loops. Another example, this is from modeling of a stroke from a very important paper that appeared in the International Journal of Intelligent Systems, IGIS, in 2007. This is from stroke expert Dr. Kathy Helgeson and Ron Yeager and others, a model of clot formation. This is one of many. There's been an extensive amount of cognitive maps, and my understanding is, I had nothing to do with it, there's going to be an international journal of fuzzy cognitive mapping coming very soon. Well, here's where that philosophy degree really came in handy, because the idea was, if I'm modeling causality with an arrow, how much a fuzzy set, something that matters, changes with degree, Ci, increases or decreases something J, how would it change in time? What would be a learning law? And without understanding at the time Hebbian networks, I came up with this idea of putting the dots over the concepts, and later called it the differential Hebbian. But this came, and with attribution, from the great philosopher John Stuart Mill, who wrote in the earlier part of the 19th century, the first book on the scientific method and what we today would call philosophy of science. In particular, Mill had 4 methods for estimating causality, and one of them, the one that's really endured, is called the method of concomitant variations. If I observe something Ci changing followed by changes in Cj, I tend to impute a causal connection, versus if they're just both on, like you would have in simple Hebbian learning. I interpreted concomitant as a product, variation as a time derivative, and lo and behold was born a version of the differential Hebbian learning law, which, by the way, also has applications, and I did not foresee this, in synapses. It's called the theory of the differential synapse. But it gives you a kind of arrow of time. That's one of the reasons it's become quite popular to use time series data to grow causal edges. We can also get them, as I'm going to show you, by asking experts for those causal edges. Now, what if I get m many experts and they give me their edges and I want to add another expert? Well, there's an easy way to do that recursively. And these are basic results that come out of statistics for updating the mean of the edges. And of course, I can weight them. And there's sample variances. And there's square root being the sample standard deviation. They have that predictor corrector form like a Kalman filter. Very efficient mathematically. Very easy to do. And it scales, as I'll get to. Now, what's not so easy is to figure out how to use these things and what they mean. The minute I have feedback, even if something as simple as this 6-node cognitive map, I get fairly complicated dynamical systems. So let's suppose I turn on the weather. In the simplest case, it's on or off. I can make that 1 or 0. I can certainly do a fuzzy hold on that. But we tend to do policy variables. So we would say if the weather went bad, we would put in the value 1 and keep that clamped on and let the system reach a new equilibrium. And then that would be the prediction. And then after that, we may take bad weather off, go from 1 to 0, and the system will converge to a new equilibrium. If I take the simplest non-trivial case of just 2 nodes, I end up with this state space representation. So the state of the system is a point in the hypercube. It's a fuzzy set of sorts. But that's not the sense in which I mean fuzz here. It's the fuzz in the causality, in the directed graph, that really matters. The directed graph here is not 1 or 0, like in the case of the Bayesian DAG. It's gray. And I get now, through the pullback, I get here 4 different output regions. So I get, in effect, 4 meta rules. For example, if I pick any kind of input in this upper region, it will map to this fixed point blue dot. Pick something in the pink region, it will map to this different blue dot in C. Pick something in the orangish, yellowish region B, it will map to this limit cycle, which, by the way, is the most common in applications. Or even in some cases, depending on your dynamics, it can map to an aperiodic attractor that's truly chaotic. So it's a way of saying if input, then one of these 4. It's a kind of meta rule, and it creates its own form of explainable AI out of these complex causal networks. Back to my Dolphin example, I have a simple 5-node cognitive map. And I can then represent that fuzzy causality through the causal edge matrix, where the causality is between 1 and -1. Here, just extreme trivalent values, full causality increase, full decrease, or none at all. Don't worry, there's a natural way to get more representative fuzzy values with sample size, because with cognitive maps in general, expert sample size is a good thing. But what do those limit cycles look like? Well, here's a much more complicated 10-node Dolphin map. No way can I think you easily trace through the causality. If we let it swirl, and here we're using simple threshold nonlinearities for the nodes, you can greatly extend this and put time lags. There are literally thousands of papers on this now, a lot of software. Then I get, when I stimulate the pattern here, dolphins are resting, then they feed, then they play, and they rest. Quickly, I lock into a limit cycle. You can just see it geometrically, the 3 increasing white squares, and they repeat. I get something that repeats. The fuzzy cognitive map, at least the way they're configured today, unlike the DAG, does not give you a nice numerical probability of a particular node. It gives you a pattern prediction. What's the pattern? Some looping bit of feedback, some sequence of states like this. For my money, the best example to date that I have seen, and I look at this, is the Brexit fuzzy cognitive map from the University of Cambridge. At Cambridge and the University of Leeds, recently some experts in energy market wanted to model the effects that Brexit, the United Kingdom leaving the European Union, would have on the energy market, water demand, and things like that. They ended up with, after some bouts of cognitive mapping, as they called it, I want to stress I had nothing to do with this, I'm just an outside observer, with a very complex 29-node cognitive map, and you're looking at it. I'd like you to think how difficult this would be to do or interpret with the old DAG model. The nice thing about cognitive maps, experts can just draw their causal picture, and we can combine them, and they did, as I said, 2 bouts of that. We're not force-fitting the system to limit it to lack of cycles, for example. Without cycles, there's no interesting feedback. And they came up with some results you can look at in their map, but it's the knowledge engineering of this that I was so impressed by. 29 nodes, practical, and what else would they use? Here's something, an ongoing project I did with my colleagues at the Rand Corporation in Santa Monica, which incidentally is where fuzzy logic began. The great Richard Bellman was there, dynamic programming fame. He had his best friend, Lotfi Zada, visit him over the summers, and over the summer of '64, that's when they came up with fuzzy logic, and you can see the first 2 papers, first published in '65 by Lotfi, which refers back in its first footnote to the October '64 joint paper with Bellman and Calabanzada. Anyway, it comes out of Rand, and Rand does a lot of policy modeling, and we were interested in a very popular model in modern political science out of Harvard's Kennedy School of Government from Professor Graham Allison. He calls it the Thucydides trap, in honor of Thucydides, the author of the History of the Peloponnesian War. And there's various articles you can see on this. I refer you, if you're interested, to our post on this called Beyond DAGs. You see it at the bottom. And the software on GitHub. The problem with cognitive maps in the past has really been simply the lack of the software. That's no longer an issue. Thucydides, as you'll recall, tells the story of how the city-state of Sparta went to war with the city-state of Athens. Athens lost that, one of the great books of history. And in one passing sentence, Thucydides says why he believes they went to war, that there was a bigger power, in this case Sparta, and it got suspicious of a growing power, Athens. Now, Graham Allison has turned this into a book. You can also read his article in The Atlantic. Here's his quote in blue: "When a rising power threatens to displace a ruling power, the most likely outcome is war. 12 of 16 cases in which this occurred in the past 500 years ended violently." So the question he asked is, with the United States, the world's dominant and arguably only superpower, and with China growing, becoming a superpower, will they go to war? Now, I don't know, maybe you don't know, but we were sure curious to see what would happen if we translated the text, knowledge engineering fashion, of Graham Allison, the expert on the subject, into a cognitive map. And here you can see some of the knowledge engineering, that we have a given causal link, in this case to war, and we go page by page to document in good legal fashion precisely what text we allege gives you that implication. And rather than just make it up on our own as we go. This also appeared in a recent volume of Wiley, put out by the RAND Corporation, sponsored by DARPA, on new techniques in the social sciences. The idea of DARPA was things have stalled in the social sciences, we want to jumpstart them. One of the techniques popular is cognitive maps, among many, many other things. We ended up with different maps. Here's a 17 node map, and you can see some of the limit cycles on the side. The big picture of this, we found, was that war did result in about 80% of the input scenarios. And that has to be interpreted very carefully. First off, when we say war results, we mean the prediction of the cognitive map based on Graham Allison's work and the more general work also at the Thucydides trap project at Harvard, is that we had limit cycles that had the war node in them. And by the way, in the non-war nodes, it tended to be the case where there was a lot of economic cooperation. 80% of the cases, I must tell you, this very much worried the folks at RAND. We had to make clear, we did not weight the relative probability of the input state. So we are not saying that there's an 80% probability that the US and China will go to war. I certainly don't know. We were just saying what proportion of the states would lead to that. We also looked at how robust the model was. So you can do this in a variety of ways with the new software. We took the cognitive maps and we shook them. We added noise perturbations. We still got that result. My last point in this talk is to open the door to what I call big knowledge. It's one of the earlier goals of cognitive mapping. We want to combine essentially everything in the human experience that we represent as knowledge: books, articles, legal depositions, informed talk. We want to have, in effect, translation devices that take us from what experts thinking or saying in the models into some kind of knowledge network that may have, for example, mixtures and systems like that involved in the individual edges. How would you do that? After all, if I get a bunch of experts, here's KM together, they're going to talk about different kinds of concepts. But the trick is there's a total number of such concepts. Let's call that capital N. And so really all the experts are talking about all N concepts. They're just saying, a lot of them are saying that there's no causal connections among some of them. What does that mean? That means I can now represent the causal matrices, the F1s. I can represent these causal matrices by N matrices, conformable for addition, by zero padding. If the first expert is missing the second concept in that listing, then the second row and column will be all zeros. I can then easily mix these, in the simplest case, add or average them to an output cognitive map. So I work with the expert domain with words, drawing pictures. They don't need to understand anything about the mathematics involved. And then with the software, very easily, we convert that to matrices. From matrices, we combine in a variety of bewildering number of schemes today. And the net result is a cognitive map. And that's often repeated in cognitive mapping sessions, what's called a Delphi session. So everybody then looks at the result and we see what happens. One of the great things about cognitive maps is they scale. They don't have that NP hard problem with DAGs. Almost all the computation is vector matrix multiplication. So the limitation here is simply n squared. And these tend to be, the combined matrix tends to be a very sparse matrix. As I showed you, there are recursive formulations. So it scales, it iterates, and you can just keep on going and growing different maps. Here I've got 3 binary maps, a total of 6 nodes, although each expert is talking about only a subset of those nodes. I can ask the experts questions. Do you think there's an edge here or not? Let them draw the picture. And it's a lot easier in general to get yes, no in terms of an edge. And now use the law of large numbers to combine these into a 6x6 matrix, into a 6-node cognitive map, where I have natural weights reflecting their expertise. And of course, I can weight the experts accordingly. So rather than be afraid of large expert sample size, this technique depends upon it. And there's some various theoretical results underpinning it. Last substantive slide, big knowledge. I can connect together different maps. I can use, for example, the power of fuzzy approximators just to estimate one of those arrows. I can glue together arbitrary numbers of these cognitive maps. I have to have maybe more efficient matrix schemes in some cases by one node triggering other maps. So it's a powerful technique for combining knowledge. Is it done? It's not even close to being done. There are many, many problems with this technology, and that's what's driving the research. One of the biggest ones is, how do you do backward inference? The kinds of inference we're doing here are, like with the case of the weather map, is a what if. What if it's bad weather? What if it suddenly goes good weather? It's much more complicated to ask a why question. Why did I observe this particular output? You can get that through checking input states, but we really don't have a good backward chaining method given the nonlinearities involved. We also, unlike the DAG case, don't have a good, really hardly any kind of uncertainty to put on the output equilibrium. We also have essentially no theory to help us estimate missing nodes. So in sum, additive fuzzy systems, which are the overwhelming majority of rule-based systems in a variety of formulations, give rise to a mixture, and mixtures can give you back an additive rule-based systems. And a lot comes with that mixture: the Bayesian posteriors, the conditionals, all the moments, and more. You can always represent any bounded function just by mixing two normal curves. The big point on mixtures for data fusion is the closed property that a mixture of mixtures is always a mixture. And then in the feedback case, the more general case, especially for causality, mixing cognitive maps also gives you back a cognitive map, so they are closed under mixing. But we're missing a lot of things: that theory of uncertainty of the output equilibria, the backward chaining structure, the why versus what if, and so forth. So I hope I've made some progress to making the case that the fuzzy field, at least on this additive component of research, is just getting going. Thank you.